I'll mainly be talking about a new viewpoint on quantum cosmology, which has implications for singularity resolution, but it's motivated by something more observational, or a problem with observations in quantum gravity, or conundrum, which is that we are dealing with an interacting theory, quantum theory, many degrees of freedom, because it's a field theory. And we know from other areas like condensed matter physics that we need approximations and different kinds of assumptions to derive something. And it's usually difficult to find good approximations, or to show that an approximation is good, if we don't have observational guidance. So because there are new effects, emergence, and what they call Moore is different in condensed matter physics. If we don't get a hint from observations, we usually don't just guess a good approximation. So that would indicate that we just shouldn't talk about observations or potential effects in quantum gravity. But the problem is, to get observational input at some point, we have to do phenomenology, because we have to know where we should be looking for potentially observable effects. So we need observations to get a good approximation, and we need a good approximation to get observation. There's a chicken and egg problem here, which is hard to resolve. But also, if we refer to other areas, there's an approach which is called effective field theory, which uses some of the ingredients that can be derived and tries to combine them or arrange them in a way which parameterizes a large class of potential outcomes. Now that's vague, but one can try to develop such a formalism and see what it implies. And in this talk, I'll present a few ingredients mainly related to singularities. There are other implications about more other space-time effects like covariance or even observations. But I'll mainly focus on quantum cosmology and the singularity question. So I'll talk about Minisuperspace approximations. That's one ingredient. The BKL scenario will play a role, and something which I'll explain in more detail, infrared regularization, which I guess is new. The other ingredients are standard, but regularization is usually not mentioned. I'll develop the main ingredients mainly based on a simple, well-understood example. It's just scalar field theory on Minkowski. That's the canonical Lagrangian. There's some self-interaction potential here. And so that's the field theory. So phi here still depends on x and t. But we can develop a mini-superspace formulation just to try to understand mini-superspaces by restricting phi to a spatially constant configuration. So that's our mini-superspace Lagrangian, where the gradient terms disappear. And the integration is just replaced by multiplication with a constant coordinate volume V0. So that would be the mini-superspace model. Now, if we just start here, mini-superspace quantization, we derive a momentum, which has the same V0 factor here. That's the Hamiltonian, which can be quantized straightforwardly. And we see that V0 appears in the kinetic and potential term in different places. It's like rescaling the mass if we change V0. We know that quantum corrections depend on the mass in standard quantum mechanics, so here they should depend on V0, which is our first lesson, which I'll reinterpret in different ways. So quantum mechanics, quantum cosmology, because it depends on V0, not just the metric, but also the size of the region. It's really a quantum theory of regions, or if we take a more constructive space-time picture of patches, homogeneous patches in an inhomogeneous geometry. It's not a quantum theory of just the metric or the scale factor as it usually appears initially. So this statement, derived from a simple consequence, will play an important role. Now, physical effects. So in this context, we have different kinds of approaches to derive effective potentials. I'll just mention the results. In the mini-superspace, the first order H-bar correction looks like this. If you don't recognize this, if phi is, or W is quadratic for the harmonic oscillator, W double prime is a constant, so that would just be the 0-point energy added to the classical potential. If W is not quadratic, there's a phi-dependent quantum correction, so it's a more complicated effective potential. In the full theory in this case, so back to the scalar field theory, there is an effective potential derived by Coleman-Weinberg some time ago. Looks very different initially, but it turns out one can do the K0 integration here exactly without any cutoffs. And the result is just a spatial K integration with a square root of W double prime, which looks much more like the Minisuperspace result. Except there's a K dependence here, the modes for the field theory. But we can now just take these two expressions here. And they are very similar if we ignore large K contributions. So if we just look at the infrared contribution, so that means long wavelength, small k, then we can ignore k compared with W double prime. So it's just our original square root. And we can replace the integration over modes by multiplication with the k volume, which is proportional to 1 over V0. And up to a numerical factor, because these are slightly different approximations, we get the same correction. So in this context, we actually do have a relationship between a mini-superspace model and a full theory regarding predictions, first order effects in H bar. And that allows us to make the usual mini-superspace truncation more precise. So we don't just have the mini-superspace result, we know how to compare it with a field theory result, and we know what kind of approximations are required in this step here. Just what I mentioned. We just take the infrared contribution and replace integration by multiplication with the volume. Now, gravity is more difficult because it has zero mass excitations, gravitons, so the infrared behavior is more complicated. In this example, that would mean we are looking at a situation in which W double prime is actually small, not large, so this expansion in K is more difficult. If W double prime happens to be less than some of these infrared modes, then we get more complicated behavior, inverse K terms, for instance. But the problem is that it's really both K and W double prime, which are small if it's an infrared problematic theory, and we're looking at the infrared contribution. But there are more refined techniques, and I think it's still being debated what the precise analysis is, but there's one recent result using functional renormalization methods, which also produces a 1 over K term. So there seems to be something relevant in this expectation here. And it's not, it's actually just the 1 over K term plus positive powers. It's not a full series in inverse powers. So it is simpler than it actually is suggested by this argument here. Now to see how that's related to quantum cosmology, so a little more technical here. I'll use the standard scale factor and time derivative canonical momenta, but I'll try to parameterize these variables in different ways because different models sometimes use different choices of canonical variables. So this parameter x here, which is just a constant, usually between 0 and -1/2 if you compare with specific examples, just describes all kinds of canonical theories. We'll also have to know the behavior of quantum fluctuations because that's where these H bar terms come from. And also here I assume a second constant y, which tells us how delta Q depends on A, which is possible, or what we're really interested here is the V0 dependence. Now, with these assumptions, then the uncertainty relation tells us what the second canonical fluctuation should be. So the uncertainty relation is standard. There's no V0 anywhere. And so that means if delta Q has a specific behavior, delta P has a behavior which can be derived. Now, completely independently of Hamiltonians, any correction to a Hamiltonian just by dimensional arguments has to be of this form if it depends on delta Q, or it has to be of this form if it depends on delta P. A Hamiltonian is proportional to V0, so that's where these V0 factors come from. And then everything else has to be dimensionless. So there's really nothing else we can do other than these two combinations. If we insert the combinations here, the assumptions, then the behavior is actually quite nice because it's in both cases a power of k, and for the q term it's just the inverse of the p term. So unless the exponent is 0, or x plus y equal to a quarter, we have at least one inverse power, which is what we expected here for an infrared problematic theory. So even though this here is just mini-superspace, doesn't really know anything about massless excitations or gravitons, it seems to agree with what the full theory here tells us. So again, an agreement between mini-superspaces and quantum field theory. So just a few details here to motivate the relationship. Now, implications. So as I emphasized, I think already twice, there are two assumptions in our mini-superspace approximation. We include only the infrared mode, so only small k in this context, depending on the size of our averaging volume. And we replace the mode integral with just multiplication with the k volume, which is a better approximation if the k volume is small, so that means large V0. So the two conditions here in terms of V0 is that we should be looking at regimes in which we have relevant inhomogeneity on scales greater than some V0. That's usually the case, but also V0 has to be large, and that's a much more important assumption, which is fulfilled in late universe cosmology, certainly, because that's the standard cosmological principle. So in this case, we can trust mini-superspace quantum mechanics. There's really an approximation behind it, not just a truncation. But we're usually more ambitious and want to extend this to early universe cosmology and approaching the singularity. Now, when that happens, usually collapse implies that we have growing inhomogeneity even within a co-moving region, so even within one of these constant B0 regions. So it's not just the like the contraction of the scale factor during collapse which pushes structures closer to each other. It's not just this, it's also within a single co-moving region. So if we ignore the time behavior of the scale factor, inhomogeneity grows. So in order to maintain the first condition here, we have to make sure that V0 is sufficiently small, so the relevant inhomogeneity is still on scales greater than V0. So we have to shrink the size of our averaging region as we approach the singularity. That's what I call infrared renormalization, because it's the scale of our infrared contribution. It has all kinds of consequences in quantum mechanics, which I can just indicate here. In quantum mechanics, shrinking the averaging region really means we have to re-average our states. So if we start with a pure state, then usually after the first shrinking process, we get a mixed state. So that's something which should be included in mini-superspace models. There's no unitary transformation to change V0. It's not even a canonical transformation classically, so we cannot do this process on a single Hilbert space, and that's why effective field theory is required here in more technical terms, because it allows us to describe this whole family of Hilbert spaces corresponding to shrinking V0. Now, once we get close to a space-like singularity, asymptotically, we can use BKL, and that's a standard argument in quantum cosmology. It tells us that we can still use homogeneous geometries, something like Bianchi 9, generically, even close to a space-like singularity. But the problem is that there's no lower limit placed on V0. So it's an asymptotic statement. It just tells us something about the geometry at a single point. It doesn't tell us that there's actually a full whatever V0 is for a Bianchi 9 model, the volume of SO3, that's not what we get. We just get a statement about the metric. So at this point, the distinction between quantum mechanics of the metric or quantum mechanics of the whole region is relevant. We need quantum mechanics of regions, so we need to bring in V0. And that means we're really talking about a local Bianchi 9 geometry, not a full Bianchi 9 model. It looks like a technical difference, but it has important consequences. I'll illustrate this in models. But the main general lesson here is that the mini-superspace approximation gets less and less reliable as we approach a singularity, because the second condition here will eventually be violated. We can't do BKL and large V0. It's just impossible. Examples, we'll hear more about all these, I think, but just the equations which are relevant for these V0 terms, that's Bohmian quantum mechanics. So there's a Hamiltonian like this, which implies a quantum potential. I'll just use these two equations, and hopefully there will be more explanations in the next few days. If we bring in V0, in this context, usually models use a logarithmic scale factor. So it's just like our standard scalar model, actually. So V0 only appears in the kinetic term. There should be a 1 over V0 squared. Each momentum gets a 1 over V0. So the quantum potential has an F here. The two square roots the V0s cancel out. So the quantum potential behaves like 1 over V0 squared, which just from the perspective of this term is a good thing, because as we shrink V0 in this infrared renormalization, the quantum potential becomes more and more relevant. And it can be used in some cases to derive a bounce in quantum models, which don't appear classically. So these bounce models are more secure if we use smaller V0. We still have to keep in mind that the Minisuperspace approximation gets worse as we get closer to the singularity, but at least just taking a Minisuperspace model in this context, shrinking V0 helps. Another example, affine quantization applied to quantum cosmology. There's an effective Friedmann equation which looks like this, two new terms compared with the standard Friedmann equation, first row here. In this paper, that's actually derived from the harmonic behavior of the anisotropies. And just citing from the paper, the term looks like this. Now that looks exactly just the qualitative behavior like our general result here. So harmonic means that W double prime should be a constant. That's this n plus 1 here. And the rest, there's an h bar over V0, just what we expect based on these general arguments. And there's a second term here which goes like, if you plug in this L, it goes like h bar squared over V0 squared. And that's a positive term on the left, so it's repulsive and also can be used to get bounces. Again, if we now use small V0 in this paper, V0 is contained in the equations, but it was assumed it's the actual volume of the Bianchi 9 configuration space. So it didn't shrink. There's no infrared renormalization. But if we just combine these two results, then the 1 over V0 squared term should be more relevant than the 1 over V0 term. So the repulsive contribution is enhanced. And also here the bounce is more secure in this effective picture. The problem is only, which I didn't find answered in these papers, is that we are really talking about a next order effect in the h-bar approximation or the h-bar expansion. So if we go to small V0, then we should also be concerned about potential h-bar squared over V0 corrections to this row of A here, which could compete with the repulsive term. Or there could even be higher order terms, which would be even more dominant. So I think that's a question which still in this effective picture needs to be answered. Final example, loop quantum cosmology. There's an effective equation of this form. And using the parameterization I had before with this x here, the density scale looks like this, depends on V0. Now, following this paper here, most of the analysis since that time have been done using large V0 because the argument was you want to produce the correct semi-classical limit at late times. And at late times, we can assume that V0 is large. But then following this model with the constant V0 all the way to high density, to the Planck density, or until it bounces with this effective Friedmann equation, is a large assumption which strongly restricts the relevant initial data. Because again, if it's collapsing, usually we have increasing inhomogeneity even within a co-moving volume. So we should combine this with this infrared renormalization. And then there are two different cases. If x is greater than -1/2, then the situation here is very different from what we saw in the first two examples. So this quantum gravity row here is proportional to an inverse power of V0, but the Friedmann equation has 1 over the scale. So in the Friedmann equation, the new term is actually proportional to some positive power of V0. So if we shrink V0, the extra term here gets smaller, not larger as in the previous two models. So quantum effects are weaker with our infrared renormalization. And the bounds, in this case, becomes less secure. So it's a very different situation from these fluctuation effects. What's usually used in this context nowadays is actually a borderline case in which x is equal to -1/2, and then rho qg is independent of V0, so that effect does not happen. But if one looks at more details, there should also be fluctuation corrections in here, which are ignored in this version of the effective Friedmann equation. And for small V0, the solutions are much more sensitive to quantum fluctuations. And it's possible to show that non-bouncing solutions actually exist. So that's also a big difference from what one usually gets for large values of V0. So to conclude here, so that's we're just a few aspects of this effective field theory picture relevant for singularities. There are other implications related to covariance, for instance. And but just focusing on the results here. So one of the interesting applications is we can really distinguish between different types of quantum effects. In some cases, usually effects based on fluctuations like Bohmian or affine quantization. These quantum effects are enhanced by the effective picture. Loop quantum cosmology is the only example I know where the opposite happens. So these are not fluctuation effects, which give rise to a bounce, and they are less secure in this picture. But independently of examples, this framework also highlights the main problem which we are facing in quantum cosmology. We usually have to rely on something like BKL type arguments just to maintain our homogeneity assumption. But for small averaging regions, large curvature, that's usually not consistent with the infrared truncation, because we're really using an infrared contribution, but we are pushing the infrared scale all the way into the ultraviolet, and that is problematic. So that underlines the difficulties which mini-superspace quantizations usually don't show, but if we try to compare that with something more inhomogeneous, it ends up to be problematic at some point. So I'll stop here and take questions.
So I maybe misunderstood, but it seems to me that your quantum effects, so depends on the size of V0. At V0, it's not a deep invariant quantity. It just depends on your coordinates, right? It's the integral.
Yeah, I focused on V0. If you look at these variables, it's always V0 times A cubed, which actually appears. So it's really the size of your averaging region. So it is diffeomorphism invariant, but it depends on the choice of your averaging region, which is a physical input depending on the scales that you want to consider.
Sure. Okay, but you always have this.
Yeah.
Sorry, I didn't say. Okay, you always have.
Yeah, I didn't mention. Because it's technical, I went through it quite quickly, I think.
So, just to ask a question, so is the interpretation of your results is that one has to be very careful when refers to the quantum effects and say that quantum effects will resolve the problem with the existence of...
If it's mini-superspace, yes. So one should go beyond mini-superspace. So in this case, one could try to, if we know a little bit more about the full theory, we can try to do a more precise expansion of the actual integral here. So including higher orders of k, which would be additional inverse powers of V0, or also higher order h bar effects. But then we have to know more about quantum gravity, which is another problem. But I haven't really used this much in midi-superspace models yet, which should be a mixture of this kind of infrared contribution for the modes which we do not include in the midi-superspace model. But some of the modes are fully included in such a contribution, really as a field theory, not just as an infrared contribution. And that could probably tell us more where we should be looking for additional corrections of pure mini-superspace effects.
Okay, final question.
You just mentioned that if one takes into account those volume corrections, the bounds in cosmology can have can be related by the solutions that.
I'm sorry.
If you take into account the volume corrections, you're saying that solutions different from the bounds are possible. But would those be singular, or can you say something about those solutions?
Do you mean inverse volume?
No,
Or just these additional terms in here?
Just go to the last slide where you speak about the bounds.
The last, the loop slide?
Yeah. Then you say non-bouncing solution do exist.
Oh, this last line here.
What
Yeah.
kind of solution those would be? Singular? Can be singular?
They would be singular in the mini-superspace model. It's a little bit tricky because once you get into fluctuation terms, you're really sensitive to quantization ambiguities like factor ordering. So one possibility is that the Koch type solutions, which you get here, so if you, it's actually a Koch of the scalar field, not of time, but that could be replaced by a Sinh. Because with fluctuations, usually you could, the identity Koch squared minus Sinh squared equal to something. That plays a role, which might push you into the Sinh behavior instead of the Koch behavior. I mean, I can show you more details privately. It really requires a lot more equations to show this. But it's like replacing a Koch with a Sinh, which goes through 0. And I guess then it's a different question. Then you would have to really understand the space-time geometry to be able to say something about curvature invariance. And space-time geometry is also affected by these quantum corrections. So it just gets more tricky. It makes the usual argument which you get from the Koch more complicated, that's for sure. And it looks more singular, but anything else beyond that requires knowledge of space-time effects, which we don't have yet.